In abstract algebra, a group isomorphism is a function between two groups that sets up a one-to-one correspondence between the elements of the groups in a way that respects the given group operations. If there exists an isomorphism between two groups, then the groups are called isomorphic. From the standpoint of group theory, isomorphic groups have the same properties and need not be distinguished. Definition and notation. Given two groups and a group isomorphism from two is a bijective group homomorphism from G to H. Spelled out, this means that a group isomorphism is a bijective function such that for all U and V and G it holds that the two groups are isomorphic if there exists an isomorphism from one to the other. This is written. Often shorter and simpler notations can be used. When the relevant group operations are unambiguous, they are omitted and one writes. Sometimes one can even simply write G equals H. Whether such a notation is possible without confusion or ambiguity depends on context. For example, the equals sign is not very suitable when the groups are both subgroups of the same group. See also the examples. Conversely, given a group, a set H, and a bijection, we can make H a group by defining if H equals G and equals, then the bijection is an automorphism. Intuitively, group theorists view two isomorphic groups as follows. For every element G of a group G, there exists an element H of H such that H behaves in the same way as G. For instance, if G generates G, then so does H. This implies in particular that G and H are in bijective correspondence. Thus, the definition of an isomorphism is quite natural. An isomorphism of groups may equivalently be defined as an invertible morphism in the category of groups, where invertible here means has a two-sided inverse. Examples. The group of all real numbers with addition is isomorphic to the group of positive real numbers with multiplication. Via the isomorphism, the group of integers is a subgroup of, and the factor group is isomorphic to the group of complex numbers of absolute value 1. An isomorphism is given by for every x in the Klein 4 group is isomorphic to the direct products of two copies of, and can therefore be written. Another notation is DIH2, because it is a dihedral group. Generalizing this, for all odd n, DIH2n is isomorphic with the direct products of din and Z2. If is an infinite cyclic group, then is isomorphic to the integers. From an algebraic point of view, this means that the set of all integers is the only infinite cyclic group. Some groups can be proven to be isomorphic, relying on the axiom of choice, but the proof does not indicate how to construct a concrete isomorphism. Examples. The group is isomorphic to the group of all complex numbers with addition. The group of non-zero complex numbers with multiplication as operation is isomorphic to the group S1 mentioned above. Properties. The kernel of an isomorphism from 2 is always e.g., where e.g. is the identity of the group. If is isomorphic to 2, and if G is abelian, then so is H. If is a group that is isomorphic to, where F is the isomorphism, then if A belongs to G and has order n, then so does F. If is a locally finite group that is isomorphic to, then is also locally finite. The previous examples illustrate that group properties are always preserved by isomorphisms. Cyclic groups. All cyclic groups of a given order are isomorphic to. Let G be a cyclic group and n be the order of G. G is then the group generated by. We will show that define, so that, clearly, is bijective. Then, which proves that. Consequences. From the definition, it follows that any isomorphism will map the identity element of G to the identity element of H, that it will map inverses to inverses, and more generally, nth powers to nth powers for all U in G, and that the inverse map is also a group isomorphism. The relation, being isomorphic, satisfies all the axioms of an equivalence relation. If F is an isomorphism between two groups G and H, then everything that is true about G that is only related to the group structure can be translated via F into a true ditto statement about H, and vice versa. Automorphisms. An isomorphism from a group to itself is called an automorphism of this group. Thus, it is a bijection such that an automorphism always maps the identity to itself. The image under an automorphism of a conjugacy class is always a conjugacy class. The image of an element has the same order as that element. The composition of two automorphisms is again an automorphism, and with this operation the set of all automorphisms of a group G, denoted by AUT, forms itself a group, the automorphism group of G. For all abelian groups there is at least the automorphism that replaces the group elements by their inverses. However, in groups where all elements are equal to their inverse, this is the trivial automorphism, e.g., in the Klein 4 group. For that group all permutations of the three non-identity elements are automorphisms, so the automorphism group is isomorphic to S3 and DIH3. In ZP for a prime number P, one non-identity element can be replaced by any other, with corresponding changes in the other elements. The automorphism group is isomorphic to ZP-1. For example, for n equals 7, multiplying all elements of Z7 by 3, modulo 7, is an automorphism of order 6 in the automorphism group, because 36 1, while lower powers do not give 1. Thus this automorphism generates Z6. There is one more automorphism with this property, multiplying all elements of Z7 by 5, modulo 7. Therefore, these two correspond to the elements 1 and 5 of Z6, in that order or conversely. The automorphism group of Z6 is isomorphic to Z2, because only each of the two elements 1 and 5 generates Z6. So apart from the identity we can only interchange these. The automorphism group of Z2 times Z2 times Z2 equals DIH2 times Z2 has order 168, as can be found as follows. All 7 non-identity elements play the same role, so we can choose which plays the role of. Any of the remaining 6 can be chosen to play the role of. This determines which corresponds to. For we can choose from 4, which determines the rest. Thus we have 7 times 6 times 4 equals 168 automorphisms. They correspond to those of the Fano plane, of which the 7 points correspond to the 7 non-identity elements. The lines connecting 3 points correspond to the group operation. A, B, and C on one line means A plus B equals C, A plus C equals B, and B plus C equals A. See also general linear group over finite fields. For abelian groups all automorphisms except the trivial one are called outer automorphisms. Non-abelian groups have a non-trivial inner automorphism group, and possibly also outer automorphisms.